Okay, in this video, we're going to look at finding the absolute max-min values on a closed boundary. So this is related to the finding the local extrema, except we want absolute max and min values. And what we mean by a closed boundary. So if we were looking at this function in its entirety, right, it might have some local max and local min points, but it might not be an absolute max. It might go up forever or go down forever, right? But if we look at this function on just a closed boundary, and so here's what we mean by this. If our domain, okay, is all the points where the absolute value of x is less than or equal to 1 and the absolute value of y is less than or equal to 1, which would really just describe numbers, x values between -1 and 1 and y values between -1 and 1. So this is like a square. So the way to picture this is, imagine you're in a room where this is your floor. You're looking at a top view. This is the floor of the room, and the function is the ceiling, okay? So you've got, most ceilings are flat, right? In a room, you have a rectangular floor and a nice flat ceiling to it. So all the points on the ceiling have the same height. But for a function like this, right, it might have a curved ceiling to it. You might have a high and low point somewhere in the middle of the room or something like that. And so what we're looking for is where is the highest and lowest points of the ceiling? That's what we're looking for when we're looking for the absolute max-min values. And if it's on a closed boundary, it's guaranteed to have a highest point and a lowest point. So then we start thinking about where could that occur? And there's some different situations. Suppose that the ceiling kind of peaked up at the top. Maybe it was like at the top of a sphere or something, right in the middle of the room, right over the origin, let's just say, right? Well, if that was the case, then that max-min point would come out as a critical point, right? We would be able to find it in the way we did previously by setting your gradient vector equal to 0. Okay, that would be a horizontal tangent plane there. Okay, so we would have a way to identify if you had a max-min within the middle of the room. But where else could the highest and lowest point be in the room? If your ceiling, let's say, was flat but kind of gradually increased up, and maybe it came to a peak over one of the corners, right? It could be the highest point at the corner of the room, and maybe your lowest point is at this opposite corner, right? So other candidates for where the highest and lowest point could occur would be at any of the 4 corner points in this case. Now there's a third possibility for where you could find an absolute max-min point, and I tried to draw a picture of it here. Let's say over this square you had something that kind of looked like a saddle, right? So if it looked like a saddle, it looks like the minimum point would probably occur here, but maybe even over one of the walls, right? And certainly this part of the wall y equals 1, according to my picture, it looks like the highest point would occur right there, right along that wall, okay? And yeah, maybe the lowest point occurs along the wall x equals 1. So that's the third place we have to look for absolute max-min points. So to check for extrema at all 3 of these possible places, and we're going to find candidates for absolute max-min points. Okay, so let's go back to our function. We're going to check our critical points first, set our gradient equal to 0, which is made up of your 2 partial derivatives. And I brought them out here. For f sub x, you can factor out a 2x and you get x equals 0 or y equals -1. And what we would do then for f sub y, we would one by one plug in. We know that if x is 0, f sub x equals 0. So if I plug that into f sub y right here, I also get y to be 0. So I have 0, 0 as a critical point. Similarly, if I let y be -1 and plug that into f sub y, I get -2 plus x squared equals 0, which is x equals plus or minus √2. Now, however, our boundary was, if you recall, x was between 1 and -1, and y was between 1 and -1. So because √2 plus or minus √2 is not in our domain, we're not concerned with it. Okay, we don't have to worry about that one. So the only critical point we have to deal with is 0, 0, which is right in the middle of our region, our domain. Yeah. we know the four corners of the room, so we're going to just go to the walls next. Now, how you check the walls, we have four walls to this one. One of them was the line x equals 1, and so you're literally just going to plug x equals 1 into your function. And if you did that, go back to your original function, you should get this, which reduces to a parabola. I guess that's actually plus 5. I had the 1 plus the 4. But it's a parabola, and we know a parabola that opens upward has a minimum value. And so we're interested in that point, right? We're looking for max min values. Now, the quick way to find the vertex of a parabola is to just take the derivative of it and set it equal to 0. So that gives me y equals -1/2. Now remember, I got that y value under the condition that x was 1. So that critical number I'm interested in is 1 -1/2, okay? I don't want to plug it back into the parabola. Not yet. Okay, along x equals -1, I actually get the same parabola. So I know it has a minimum value at -1/2 for y, but this time my x value is -1. If I plug in y equals 1, I end up getting this parabola 2x squared plus 5, which is also an upward parabola. And that one I just know the vertex, that's just a parabola moved up 5 units. So the x coordinate of the vertex is 0. And of course, y would be 1. The 5, by the way, that's going to actually be the z value there. We'll get to that, right? So I know it seems weird. You're saying, that's not, this isn't the vertex of that parabola in terms of, this is where that parabola is, the vertex in terms of x and y. Okay, and then along y equals -1, the x squared terms actually drop out and we just get f of x equals 5. Now, that's just a horizontal line, right? That doesn't have any extreme values. There's no mins or maxes on a horizontal line, so we don't need to worry about that particular wall. So then we make a list of all of our candidates, all the points of interest that came about. And so that's going to be on the next page. Okay. So I like to make a table. There's a lot of points. We had our critical point right here at 0, 0. This was critical point. And if you plug in 0, 0 for x and y, you get 4. Our 4 corner points to our room, our rectangular region, if you plug those in, you get 7, 5, 7, 5. Along our walls, at our critical number of 1, -1/2, you're going to get 4 3/4 if you plug that in here. And if you plug in 0, 1, you get 5. Remember, that was that wall that actually had the vertex at 5, if the parabola's vertex. So it comes out here, if you're wondering. And then I also get 4 3/4 at -1, -1/2. So now I got my whole entire list, and I can just look at this and I can say, okay, what's the biggest number? 7. So my function has an absolute max of 7, which occurs at 2 points. That's fine. And my absolute min was 4, which occurs at the origin at 0, 0. As you can see, there's a lot of work that goes into this. There's a lot of things to check. Now, some of them aren't as bad. So this one's number 17 in our book. So we want to find the absolute max min points of this function over the domain. And this time it's a triangular region where you have 0, 0, 2, 0, 0, 3. One thing you have to do, because we're going to need the equations of these walls, is you have to find the equation of the line that passes through 0, 3, and 2, 0. That has a slope of -3/2 and a y-intercept of 3. So that's how I got that line. Now, what's kind of nice about this, in terms of critical points, if I take the derivative of my function, I get 4 for f sub x and -5 for f sub y. They never equal 0, so there's no critical points. Okay, I don't have to worry about that. Furthermore, if I check my walls, if I go along y equals 0 and plug that in, I just get f of x is 1 plus 4x. That's a linear function. That's just a line. There's no What you'd be looking for are things like on the last example, like parabolas that have mins or maxes. So no extrema on that line, except possibly at the endpoints of that line, but we're going to have those covered when we do the corners. Along x equals 0, if you plug that in, you get another linear function, no extrema on that one. And then if you plug in y equals negative 3/2 x plus 3 in for y and simplify it down, you also get another linear function. So there's no extrema on that. Again, except at, right, if these are lines that are slanted, then they could have an extreme value at the endpoints of those walls, but we've got those covered. That's going to be in our list when we check our corner values, which is the only possible place then, right? We have no critical points, no extrema along the walls, so the absolute extrema must occur at the corner points. So I just evaluate my 3 corner points, and I can tell that my absolute min would be negative 14 at 0, 3. My absolute max would be 9 at 2, 0. Okay, that's how those work.